Okay, guys. Good evening. We will continue with the problem we were discussing last time, and so it was problem number 7.4. Okay. No talking here, guys. Okay. So this is the problem we were discussing. So we had it's a triangle. One, two, three, and 4, 5, 4, 5. And here it is specifically mentioned that in this element linear is 1, 2, and the others are quadratic basically. So it says construct the shape functions for the 5-node triangular element shown in figure, which has quadratic shape functions along 2 sides and linear shape functions along the third. Okay. So be sure your shape functions for all nodes are linear between nodes 1 and 2. Use triangular coordinates and express your answers in terms of triangular coordinates. Okay. So basically this once it is mentioned something that you have to meet this criteria, then you have to actually specifically design for it. Last time we just looking at the 5 of them, and we fit the Pascal triangle. Okay, so that's a good thing to do basically in that case. It's not wrong. Only thing is the requirement that was set that we could not do it. So we have to look at it and see what we can do in that case. Yeah. Okay, so first thing is we will like transfer into the system like a triangular system itself. Okay, and how did we do? In this case, if you see, we have like we can also write it in terms of different way basically, you can transfer this into triangular system. Typically what we do, we write 3 here, and then you have 1 here, and then you have 2 here, right? This is how you transfer. Yeah? So this becomes Xi1 system, this is Xi2 system, and this is 3. So if we transfer that here, what do we get? We get, this is the 5 here. Yeah. So we get between 2 and 3 we have 4, and then 1 and 3 here we have 5. Either you can write this way, or we can also look at other way as well. What is the other way? We can see that 3. We can also plan the other way as well, and that will be something like, instead of having 3 here, we rotate and we make 2 here, 1 here, and then we have 3 here, 2 here. So that way also you can do it. Okay, so why you want to do it that way? So we will see that. Okay, so we can either this, or we also can also construct this becomes number 1. Number 1 is like this. Then we have number 3 here, and then we have number 2 here. So this is xi2, this is xi3, right? And we have 1 here, and now if you see between 1 and 3 we have 5, and between 2 and 3, between 2 and 3, number 4, right? Is correct? Right? And along 1, 2, we have xi2. Yeah? Why we did like that? Because in that case we can see that this is linear in terms of xi2 or not, right? Just we can check immediately. Last time we did it this way, and we tried to check whether if you go from 1 to 2, you have a linear shape function or not. So we try to convert into S system and try to do. To begin with, if we have that, we will see that shape function, if it's a linear, it will be a function of xi2, for example, right? So it's a convenience. Basically, we can check immediately.
Actually, we had 1 and 3 line xi1 and xi1.
1 and 3 line.
Said we had xi1 there.
Acha. Okay, got it. So here, let's see here. In any case, remember that xi1 plus xi2 plus xi3 is equal to 1. Right? This is the thing. All the 3 are, one of them is dependent. Yes. So how you do? You can write any way. Basically, either you have.
So now xi1 is dependent.
Yeah. Now xi1 is dependent. Yeah. So you can write, because if you see xi3 is equal to 1, xi3 equal to 0 here. So this is xi3 equal to 1. So you can write that way. And this will be equal to xi1 is equal to 0, right? This equation will be xi1 equal to 0. That is 1 minus xi2 minus xi3 equal to 0. This is what this equation will be. Yes, you can write that. This for convenience, basically, so that we can frame accordingly. Yeah. Okay. Now we follow as we discussed earlier, and the idea here is to just see, we see the equations, right? The equation of those lines, and accordingly we can do it. The way we did earlier, just we follow them and see how it goes. Keeping in mind that when you go from here to here, it should be linear. But when you come from top to down in y direction or xi3 direction, it is quadratic. In xi2 direction, it is linear. That's what we have to do. We have to keep that in mind. So you start with from here. Okay. Now let's start from something which is quite easy. Xi3. Xi3, you can see here. Let's say this one is at . Okay, so this one is xi3 equal to, right? xi3 is equal to half. What is this one? Xi3 equal to 0. This is xi3 equal to 1. Yeah. Accordingly, we can frame immediately. We know that xi3, if you want to find out, this is one line, this is another line. We just frame like that. We get it. Yeah. This is very easy basically. So n3 is we can write xi2, xi3. It doesn't matter actually. This is we are talking about even xi1, xi2, xi3. Basically, it's a tabular system, but we write like this is equal to xi3. We write alpha here, yeah, and then we have xi3 minus half, right? And we know that when you have xi3 is equal to 1, this is 0, 1 basically we are talking about, right? So n3 0, 1 is equal to alpha times 1 times half is equal to 1 and
Alpha equals to 2.
alpha equal to 2. So n3 xi2 xi3 is equal to 2 xi3 minus half. So we get that. Next, let's look at this point. Okay. So if we are want to find out n5 xi2 xi3, then what happens? What is the equation there? You tell me two lines basically that will take care of those.
The 3 by 4 side 3 side 1.
One this and another is this one, right? One is this, one, another is this line, right? Automatically taken care of. You agree? Okay. So what do we get? Is there any other? It's the most convenient. These two, wrong, right? So what is this line?
1 minus
Side 1 minus side 2.
This is I1, you can write, yeah. This is I1, and then let's say beta, and then we have this line which is equal to
0.
this one is side 3, right? Okay, and this one n5 at 0 half is beta, and what is xi1 here? Xi1 is also half, right? So this is goes like this. So this is xi1 is also half. This is half distance from here. So half multiplied by xi3 is also half, right? So is equal to 1 and beta is equal to 4. So n5 xi2 xi3 is equal to 4 xi1 xi3. You can expand also, is equal to, you say 4 1 minus xi2 minus xi3 multiplied by xi3. Yeah, so what we see here is xi3 is quadratic, right? Okay, this is xi3 is quadratic. On here you have quadratic is one thing. We also have to look at whether like when we go from 1 to 2, then what is the behavior of that? So if you are at 3, n3, let us say n3, if you are going from 1 to 2, then xi2 moves, right? But xi3 remains constant. So in fact, n3 is 0 only, basically, throughout. So basically, it's 0 everywhere. So it's constantly 0 only, meaning that it's a linear. It falls in the definition of linear also. Right? So I mean, as such, this has to be 0 anyway. Right? A two shape function has to be 0 at all other point corresponding points, right? So it will be 0 anyway. Only thing we have to check that it is not quadratic, right? It's linear is okay, it's 0 is okay, but it should not be quadratic. Yeah. So far it is not. N5, if you see what happens, N5
It's a linear in what you are saying.
here in Xi1, Xi2, how means if you go here, the value will be something like this. 1 here going to 0 linearly, and that's what is meaning. Yeah, linear here will be either 0 to 0 linear, either 1 to 0 is linear. So linear only. It should not go like this. That's the only thing. So it's a 0 0 value, a line only. 1 0 value, line only. It should not be 0 0 here, here in middle some value. Right? In that case, it becomes quadratic.
Yeah, I was going.
So if you N5, if you see N5 also, this is Xi3 equal to 0, say N5 also becomes 0 here. But look at N3, if you go from here to here, then what happens? This is quadratic in Xi3. This is quadratic if you go this way, right? Yeah. If you, whether you go from here to here, it is quadratic, or you go from here to here, N3 is still quadratic. Because for them, Xi3
Not 0.
not 0, and hence it will go like this. N5, if you see, what happens? This is Xi1 and Xi3. So then this is N.
Xi1 is 0.
Okay, no, there is. Okay, fine. So if you see here, the Xi1 times Xi3. So if you look from here to here, we have 0. If we go from here to here, then what happens?
Xi2 is 0. Again, quadratic in Xi3.
Xi2 is 0. Yeah, so what you get? 4, 1 minus Xi3 is Xi3. So again, it quadratic is Xi3.
The other line 2, 3.
Other line 2, 3, if you see, then what happens? 2, 3, Xi3 is 0. So it becomes 0. So linear in that direction. Yeah, so far so good. Along this it is 0, because Xi3 is 0, right?
Sir, along 2, 3, it's not quadratic.
So along 2, 3.
Yes, sir.
So if you go along 2, 3,
Xi1 is 0.
no, Xi1 0 is okay. No, Xi1 is 0. Like, but N5 4 Xi1 Xi3.
The both are becoming 0.
No, it's okay. So
So is it necessary for every shape function?
yeah, probably it's not necessary.
Yes.
Yeah, I think we cannot force so much basically.
Yes, for every function.
Yeah, but still it's a 0. It's not something else basically. So I think here if you look at
Sir, I think now I don't understand the question.
you what?
Sir, I don't understand the question because is it a compulsion to satisfy only the
No,
linear
it's
edge for everything?
it's not. I mean, it's not possible that see here N5 has to 0 here, 0 here, 0 here. So a quadratic will not be 0. No, it cannot draw a line, quadratic line which is 0 here and 0 here, 0 here. The only way it has to satisfy is everywhere it's a linear 0 one. A line is also quadratic in a way, right? So a line is a subset of quadratic equation, right? The quadratic, the parabola, right? Do you agree? So I think that way from that, but you cannot actually define anything which is like 0 here, 0 here, 0 here, and it is quadratic. It's not possible. No, it's not possible. So it will be 0. Yeah. You ask question.
I was saying that for the value, if for any point in between the element, we write summation ni zeta.
Hmm.
So for the equation to be linear on 1, 2, we just have to prove that n1 and n2 are linear. Because the rest shape functions n3, 4, 5 will be 0 on the line 1, 2. So as long as n1 and n2 are linear, that will give us the answer, right?
We will see that. Okay, so as per this question, it says that all shape function has to follow the same thing.
So how can every function satisfy that on other lines it's quadratic?
So quadratic meaning that
It can be zero linear.
maybe the way it is written probably does not is not clear. Okay, so but what it means basically is what we will find out. Let's see the solution basically, and then we will compare what is the meaning. Yeah. Okay. So here, if it is along this, typically what happens? Like these shape functions are defined for the whole domain. Only at the boundary we are seeing how it is varying. That's the thing, right? And if number 5 is here, we will see here how it is varying rather than here what is varying. So I guess what it means is to make sure that n3 is quadratic here, n5 is quadratic here. That's what it means basically. Yeah. N1, if you go this way, it is quadratic, but if you go this way, it's linear. That's what it means. So accordingly, we will see. Yeah. Okay, so now N5 is there. So
Then N3 and N5 don't have to satisfy that thing on N1 and 2, 1, 2 line.
sure.
So we only have to see M1 and N2 satisfy the linearity.
That's what it means basically, I think. Okay. Again, this is the way it's written. It looks like you have to enforce for all shape function like that, but it's not possible. There it is 0, you cannot do it. No. For N5, let us say if you have a line like 0 here, 0 here, 0, N5 has to be 0, 0 here. On the same line, if you have 0 here, 0 here, 0 here, how can it be purely quadratic? It's not possible. You cannot impose that condition. It's not possible.
The imposition is only given for like be sure shape function for all nodes are linear between nodes 1 and 2.
Yeah. So, but it can be 0. For N5 also, 0 here and 0 here, then it will be 0 only, na? It has to be 0 only, there is no other way. Okay. Now, N4, if you see, then we have this line and this line. Automatically it takes care of, right? This line and this line. This line is what? N xi2, xi3 is equal to gamma, let's say. And then you have this line, xi3, and then this line and this line. This one is, so this one is xi2, this is xi3. Right? So xi2 times xi3. Yeah, and we know that N4, xi2 is half, and xi3 is also half. So half equal to gamma, half is equal to 1. So gamma equal to 4. So N4, xi2, xi3 is equal to 4 xi2, xi3. We get that? Okay. Okay, now 1. Okay, so N1, xi2, xi3 is what? Now here we have to be careful how we like write it. Okay, so although if you see we have no other option actually. If you look at, we have this line and this line, right? The way we have write it. But what happens is automatically it saves us. It makes it linear. So we will see here. So this line is xi3 minus 1. So let's say delta, and we have xi3 minus half is this, and then this line. This is xi1. Xi1. Yeah. Okay. Now this point is 1 in 0, 0. Yeah. So n1 is 0, 0 is equal to 1 is equal to delta. Xi3 is 0 minus half. Then xi1. What is the value of xi1 here? Xi1 is 1. Yeah. So basically 1. Because xi2 and xi3 both will be 0 here, right? So 1 minus this, so is equal to 1. So delta is equal to minus 2. So n1 xi2 xi3 is equal to minus 2 xi3 minus half multiplied by xi1. Okay. It's fine. Okay, now you can check n1. If it is moving this way, up and down, then what happens?
2 is 0, so this is quadratic.
It's a quadratic because xi3 you can write it like this one, equal to minus 2 xi3 minus half, and then you have 1 minus xi2 minus xi3, right? So along this xi2 will be equal to 0. So you have xi3 minus half multiplied by 1 minus xi3. So it is quadratic with xi3. If you go from here to here, then what happens?
Xi3 is 0 and xi1.
So xi3 minus half. See, so xi3 will be 0, so put 0. So this becomes, first term becomes constant. The next,
Also becomes xi2 1 minus xi2.
so here xi3 will be 0, so 1 minus xi2. So it varies with xi2 only linearly. So we get the linear function. Yeah. Similarly, n2 xi2 xi3. Here also we have this line and this line, this line and this line. Yeah, so let's say call it lambda, and we have this line is xi2 equal to 0, so we say xi2, and then xi3 minus half. Here also we can put n2 xi2. N2 xi2 will be 1 and xi3 0 lambda times 1 and 0 minus half is equal to 1. So lambda minus 2. So n2 xi2 xi3 is equal to minus 2 xi2 xi3 minus half. Yeah. So this also, since xi3 equal to half, if you for this one, if you put xi3 value, the second term becomes constant, and you will see it varies with xi3. So linearly it varies. Yeah. Okay. On the other hand, if you go this way, then what happens? The both changes. Xi2 also changing, and at the same time xi3 also changing. That's it will be quadratic. So only thing is we don't know whether n I equal to 1 to 5 is equal to 1 or not. But it will be 1 because we made sure if you look at the every point it is 1. So it is bound to be 1. Any question? Okay, we solve problem from chapter 8. I have posted two solved problem from previous to previous year. Okay, so it was during the lockdown. So it is nicely made actually, putting lot of time basically. Okay, from the PowerPoint basically. So very nicely typed, put lot of effort in that. So that's why I shared, and two problems are solved: 8.2 and 8.4. So you see that. Okay, so although we'll discuss briefly here. Yeah. So your quiz actually has chapter 6, 7, 8. Yeah. So
So 8 we haven't done in full, right?
it is done already.
No, sir, I mean, in the book, I think some parts here.
If something not covered, we are not going to cover it. Okay. Okay. So we cannot do, otherwise it will take more time. Actually, so okay. Now I'm going to erase from here so that we can solve 8.1. We will get. Okay. Consider a problem, rectangle 2 meter by 1 meter. So we have a problem which is like this. Okay. The conductivity is K is given. So K4, K is given. So I will just write which all things are given. K is given, T 10 degrees prescribed. So we write K equal to 5, S equal to 50, K equal to 4, S equal to 50. So those things are given. Q bar equal to 30. Then we have T bar equal to 10.
So
Q,
no different boundaries, Q bar is different.
yeah, so Q bar equal to 0 here. Okay, so insulated, and Q bar equal to 0 at the left side as well. Then you have A, B, C, D given. Okay, so this is the problem. Okay, and then find the nodal temperatures, nodal fluxes, evaluate the element matrices by Gauss quadrature. Use a single rectangular finite element with the node numbering shown is figure 8. Okay, so node numbering is given as this: 1, 2, 3, 4. So node numbering is given like this. Okay. Use a single node numbering like this so that the local and global node numbering coincide. Okay. So we have 1, 2, 3, 4. Use a single rectangular finite so that the local and global node numbering coincide. Anyway, Number you can change anytime, doesn't matter. Either you can start from here or anywhere. By the when you write it, then you have to write it in a proper way. You have to remember which one is that. So it's fine. Okay, now how to solve this one? Okay, so it is if you look at without using equation also, a lot of things can be found out. You can just write. So here they are finally the thing is Ku equal to F. Right? We call it a stiffness matrix, but in this case, since it is a heat transfer problem, we call it conductance matrix. Yeah, instead of a displacement vector, you call it a temperature vector in this case, and this instead of force, we call it flux vector. Yeah, that's the only difference. Otherwise, I mean, even you name it differently, but you can call a stiffness matrix or displacement vector. Still, you can use it. Is like a just relating to like a traditionally what because of its history basically. Yeah, so regardless of which problem we are talking about, we call it a stiffness matrix. Okay, now K you have to find out. We will come back later. Just we start with U, right? U is which all things we have today, right? So we have see here. We have what is the value here? So T1. T1 is equal to 10. What is the value here? T2. T2 equal to 10. So you write 10 and 10. Now what is the value here? T3. Do you know? Don't know. So you write T3. What is the value here? T4. So U is complete. Right? Now the force vector F. Now you have to look at force vector. We have starting with here. What is the value of a force vector here? Now we have two types of things here. Either there is a either coming from domain or coming from the boundary. That's the only thing. Yeah. Whether heat gain or heat loss is inside the domain, or it is heat loss or heat gain is at the boundary. Accordingly, we add them together. So basically, you write it this plus this, meaning that this is we call it Fs because of the domain, or this is because of F gamma, or you can say Fq because of the boundary. Right? Two types of things are coming. Okay, now Fs, see here, we have only one thing, S50, right? Every rate will be 50. Yeah, it's a constant. Okay, then how can you find out what is the value? Either you will do Sn, right? Xy, Ni, right? Either you can write this F Si is equal to like this, right? On a whole domain. So typically in you remember in 1D also you had something like this one. You have the source value multiplied by the shape function itself, and then you integrate over the whole term and you get it. Either you do like that, or in and at the end what you see. In this case, since it's a purely rectangular element, then it will be equal to what? It will be simply S naught into area, right? Divided by 4. It will simply S naught multiplied by area. You have 2 times 1 divided by 4 is equal to S naught is equal to 4, which will be at all the nodes. Right? See here, from the continuous system, we are transferring it to a discrete system. That means whatever is the heat produced here, we are distributing to all 4 corners, all 4 nodes, right? So S, which is watts per meter square. So multiplied by meter square area and divided by 4 because there are 4 corners, and hence this will be S naught over 2. So we get S naught over 2, S naught over 2, S naught over 2, S naught over 2. Just looking at this, just an insight, either you go mathematically or you know that this is the, you can predict that is the answer. Okay. Now FQ. This is also equal to 0. So what it says, from if you go from A to B, then Q bar is equal to 0. Actually, you did not have to mention Q bar equal to 0. It's a natural boundary condition. Even if you don't, even if you don't mention Q bar equal to 0, it's automatically taken as 0. For example, if you did not mention S equal to 0, right? Then the force is 0 automatically. When you mention F equal to something other than 0, then you need to calculate. Otherwise, you don't need to calculate. Right? The force is a flux type of thing. Yeah. So this is a natural boundary condition. So I mean, S is not a boundary condition though, but I'm saying this is something at the boundary. If Q bar is given equal to 0, that means heat loss is equal to 0. You are saying. Yeah. So if heat loss equal to 0, then what happens? That's the meaning is there is the insulator there, or there is no heat transfer from that side. Yeah. So that means there is no contribution coming from here. It will be 0 basically. Q bar is equal to 0. So due to this one, you can write between 0 and 4. Anyway, this is going to be distributed between this and this. It is like a distributed force. It is like distributed heat loss between 0. So it will be 0 divided into 2 parts, 1 and 4. It will be 0 and 0 only. So 1 and 4. So this is 1, it will be 0, 4, it will be 0. We write 0.
So the contribution is half from this and half from upward, right?
Where?
So I mean, A will be completely 0 at A, but at B it will be something from.
Right, that's why you add it. Okay. So for this also Q bar is equal to 0. It's given here. So between 3 and 4 is 0, right? So we have 1, 2, 3 is 0 and 4 is also 0. So we write 0. Yeah. Fine. Okay. Now Q bar equal to 30 here. Okay. Then what is the meaning of that? Q bar is equal to 30. When you say Q bar, that really means you are talking about heat loss, as you know, right? We said Q bar is equal to Q dot N. N is outside. It is telling you the heat is going outside, actually, right? So this Q bar is equal to 30. That means there's a heat loss. So that means, and that is distributed between 0.2 and 3. And what is the length from here to here? 2. So 30 multiplied by 2, because remember, you have Q dot N and integrated over the boundary. So multiplied by the length, right? So hence you have, if you go to 2, it will be minus 30 multiplied by 2 divided by 2. Right? And it will be here 30 multiplied by 2 divided by 2. Right? Okay. So we have seen this boundary, this boundary, this boundary. What about this boundary? 1 to 2. 1 to 2 temperature is given. Hence, we have no idea what is the flux there. And hence, there will be a reaction there. So we will write reaction here. So 1 and 2, there will be reaction. So you say equal to R1, you say equal to R2. So these are the reaction, and that's it. So this is the done. What is the next thing? Next thing is finding out the stiffness matrix, right? Does the same thing remaining, and K, as you know, is equal to BT D. Here it is a constant. Is a small k we can have. This is constant. So B transpose B D omega. So you can have K. Let us say K11 is the K11 or Kij is equal to becomes what? This becomes K small k, and then what do you get here? Del Ni del x del Nj over del x plus del Ni del y plus del dot del Nj over del y. Now you have to just integrate it, and as you know, n will be equal to what? So where n is equal to n, you can. So this we have done already, right? So you have 1, 2, 3, 4. Yeah. So accordingly, n1 has to correspond to this. Now, only thing is that, right? N1 will be this, n2 will be this, n3 this, n4 here. So yeah, if it is, let us say 0, 0. You have 2, 0. You have 2, 1, and you have 0, 1. So accordingly, you are going to formulate this one. So n1 will be equal to what? This line and this line, right? So you have x equal to so alpha. If only in xy, it's okay. Right? So this will be x equal to 0. This one, this is y equal to what? So y minus 1. Right? Where n1 to 0 is equal to 1, alpha 2 multiplied by 0 minus 1, alpha equal to minus 2. So n1 xy is equal to, oh yeah. So this will be equal to minus half x y minus 1, and so on, and proceed for all others. So that's what they did. Any question, guys? Time is 6:50, but for question 6.2, 8.2, I have posted already, so you can see that. Yeah. But just to discuss briefly here, so there are two elements. The only difference here is there are two elements. Yeah, so you have to assemble it. So this is one A B C D, A B C D, and then Q bar equal to 15x. Q bar equal to 15x. And T equal to 10 here. And insulated. It's written here. This is K1 some value. This is K2. You have to solve it. There are two basically elements. That's the only thing. You have to assemble it. Right? Once you have the separate shape function, stiffness matrix for the two elements, and then you assemble them together. Okay? The way you have done chapter 2, right? Assembly. That's the only thing. But what? Okay, I will also send you the MATLAB codes for this chapter. Yeah, so you can see how it is being implemented also. Yeah, so all these are now, it goes to programming zone because you cannot actually here, it takes like 2 classes of time if you go deriving and then solving it. But you understand that if you do programming, you can solve it. What I want to stress here is Q bar equal 15x, how to do it. So now insulated, when you say insulated, means what? Q bar is equal to, that we have seen already, right? And T is, here Q bar is equal to given like this. So how to do? So again, please have, always you think in terms of inside, so what is the inside of that? If you have 15x, then what happens? And from here x starts, equation, the x starts here only, here. So Q bar is this one, so basically we are moving like this, right? Minus, because all this says, sorry? No, this really means that this is a heat loss. That's why I'm drawing minus, right? So it doesn't matter. So what happens is A, B, C, and what is the value here? Depending on what the length, and the length is 2 and 2, right? So from here to here 2 and 2. So here this value is 30. This is 60. It's a heat loss. Heat loss, so that's why I will write minus rather. We write minus. We write minus 60. It's a heat loss. We write like that. Now, if just looking just graphically, if somebody has to find out what will be the value here of F what? FQ. Let's say call it 1, 2, 3, and 4. FQ1 is equal to what? Can you find out? If this were a distributed load, how would you do it? And you have to find out what the reaction force here. What is the reaction force here? So you have to, again, this is not a 3-noded element. They are separated. First you see from here to here and then here to here. So basically, actually it has 2 things. One is here and another is like this one. So if there is a triangular force, then what happens? What is the proportion of this area comes here? I mean the weight. Will be equal to? Will be 1/3. Okay. So 1/3 of this area, which is equal to minus 30 into half, right? Minus 30, which is this one, and then half, and then length of this. And what is the length of this? Is 2. So FQ1 is that. This is the distributed load. This one is heat loss per unit length. That's what Q bar is. Right? So per unit length, so you multiply it by length. But 1/3 of the whole area. So this is the area, and 1/3 of that is coming from FQ2 will have two contribution. One coming from here, which will be 2/3 of -30 into half into 2 plus another contribution coming from this side now.
Rectangle and 120.
Yeah. Okay, so for this, what you will do? You do like this one, half from this side and 1/3 from this side. Yeah. So basically, what you will do? You will this will be here, or so half of this will be half times -30 multiplied by 2 only. So
1/3.
half of this, right? And then plus this way, right?
Yes.
Plus 1/3 -30 multiplied by half, right? And FQ3 will be equal to
-60.
half of this, half of this, so half here, no? This also you do. So half -30 multiplied by 2, and then plus 2/3 -30 into half into 2. If you use equation, you will get the same thing. Yeah. Because Q bar is nothing but like a force only, right? It is flux. Force is also flux. That's why. That's right. Rest is the details that you can find out. Basically, you can integrate and you will see that you will get it. And how you will find out it, you will get it, because like FQ, as you know, is simply you will have here Q bar, right? So it will be minus Q bar and then N, right? In I. So you will get of this form. So automatically this will be minus. You will see that, and then N. If you say N1 will vary linearly from here to here. N3 will be 0 here, right? So if you take only one element here, let us say you have 1, 2, 3, 1, 2, 3. N3 will be 0 here. N1 will vary linearly. N2 will vary linearly. So this will behave as a 1, 2 noded element, and hence the weight we have there in chapter 3, 4, 5, same way it behave here. Yeah? And hence the forces contribution we are getting, same way we are getting. Any question? Details, please see the video that I shared, and you will get what exactly we are doing. Similarly, for other questions also, I mean, if you understood this one, the rest is just the details only, applying, putting more time, more practice. But this is what it is. Actually, implementation is very easy. It's not. We just understood some physics, we understood some mathematics, and you apply some computer science, right? Means programming, and that's what you do. You have to manage data and all kind of things. Yeah. So actually, there is not much there, but understanding how it fits the mathematics is very important. That way, if you have a new problem, so some new say differential equation you got and you have to solve it, then if you know you know how it works, then only you will be able to solve it. Right? So, any questions? Yeah. So that's it for today. Yeah. Any question, guys? Any questions from those online?
No, sir.
Okay. If there's no questions, then see you guys tomorrow at 10. Okay. Bye.